An AC motor is an electric motor driven by an alternating current. The AC motor commonly consists of two basic parts: an outside stationary stator having coils supplied with alternating current to produce a rotating magnetic field, and an inside rotor attached to the output shaft producing a second rotating magnetic field. The rotor magnetic field may be produced by permanent magnets, reluctant saliency, or DC or AC electrical windings. Less commonly, linear AC motors operate on similar principles as rotating motors but have their stationary and moving parts arranged in a straight line configuration, producing linear motion instead of rotation. Operating principles: when an AC motor is in steady-state rotation, the magnetic fields of the rotor and stator rotate with little or no slippage. The magnetic forces between the rotor and stator poles create average torque, capable of driving a load at rated speed. The speed of the stator rotating magnetic field, relative to the speed of the mechanical shaft. Otherwise, asynchronously rotating magnetic fields would produce pulsating or non-average torque. The two main types of AC motors are classified as induction and synchronous. The induction motor always relies on a small difference in speed between the stator rotating magnetic field and the rotor shaft speed, called slip, to induce rotor current in the rotor AC winding. As a result, the induction motor cannot produce torque near synchronous speed where induction is irrelevant or ceases to exist. In contrast, the synchronous motor does not rely on slip induction for operation and uses either permanent magnets, salient poles, or an independently excited rotor winding. The synchronous motor produces its rated torque at exactly synchronous speed. The brushless wound-rotor doubly fed synchronous motor system has an independently excited rotor winding that does not rely on the principles of slip induction of current. The brushless wound-rotor doubly fed motor is a synchronous motor that can function exactly at the supply frequency or sub to super multiple of the supply frequency. Other types of motors include eddy current motors, and also AC, DC mechanically commutated machines in which speed is dependent on voltage and winding connection. History: alternating current technology was rooted in Michael Faraday's and Joseph Henry's 1830–31 discovery that a changing magnetic field can induce an electric current in a circuit. Faraday is usually given credit for this discovery since he published his findings first. In 1832, French instrument maker Hippolyte Pixia generated a crude form of alternating current when he designed and built the first alternator. It consisted of a revolving horseshoe magnet passing over two wound wire coils. Because of AC's advantages in long-distance high-voltage transmission, there were many inventors in the United States and Europe during the late 19th century trying to develop workable AC motors. The first person to conceive of a rotating magnetic field was Walter Bailey, who gave a workable demonstration of his battery-operated polyphase motor aided by a commutator on June 28, 1879 to the Physical Society of London, describing an apparatus nearly identical to Bailey's. French electrical engineer Marcel Duprez published a paper in 1880 that identified the rotating magnetic field principle and that of a two-phase AC system of currents to produce it. Never practically demonstrated, the design was flawed, as one of the two currents was furnished by the machine itself. In 1886, English engineer Elihu Thomson built an AC motor by expanding upon the induction-repulsion principle and his wattmeter. In 1887, American inventor Charles Schenck Bradley was the first to patent a two-phase AC power transmission with 4 wires. Commutatorless, alternating current induction motors seem to have been independently invented by Galileo Ferraris and Nikola Tesla. Ferraris demonstrated a working model of his single-phase induction motor in 1885, and Tesla built his working two-phase induction motor in 1887 and demonstrated it at the American Institute of Electrical Engineers in 1888. In 1888, Ferraris published his research to the Royal Academy of Sciences in Turin, where he detailed the foundations of motor operation. Tesla, in the same year, was granted a United States patent for his own motor. Working from Ferraris's experiments, Mikhail Dobrovolsky introduced the first three-phase induction motor in 1890. A much more capable design that became the prototype used in Europe and the US. He also invented the first three-phase generator and transformer and combined them into the first complete AC three-phase system in 1891. The three-phase motor design was also worked on by the Swiss engineer Charles Eugene Lancelot Brown, and other three-phase AC systems were developed by German technician Friedrich August Hasselwander and Swedish engineer Jonas Wenström. Induction motor. Slip. If the rotor of a squirrel cage motor were to run at the true synchronous speed, the flux in the rotor at any given place on the rotor would not change, and no current would be created in the squirrel cage. For this reason, ordinary squirrel cage motors run at some tens of RPM slower than synchronous speed. Because the rotating field effectively rotates faster than the rotor, it could be said to slip past the surface of the rotor. The difference between synchronous speed and actual speed is called slip, and loading the motor increases the amount of slip as the motor slows down slightly. Even with no load, internal mechanical losses prevent the slip from being zero. The speed of the AC motor is determined primarily by the frequency of the AC supply and the number of poles in the stator winding, according to the relation, where N equals synchronous speed, in revolutions per minute, F equals AC power frequency, P equals number of poles per phase winding. Actual RPM for an induction motor will be less than this, calculated synchronous speed by an amount known as slip. That increases with the torque produced. With no load, the speed will be very close to synchronous. When loaded, standard motors have between 2 to 3% slip. Special motors may have up to 7% slip, and a class of motors known as torque motors are rated to operate at 100% slip. The slip of the AC motor is calculated by when R equals rotational speed in revolutions per minute. S equals normalized slip, 0 to 1. As an example, a typical 4-pole motor running on 60 Hz might have a nameplate rating of 1725 RPM at full load, while its calculated speed is 1800 RPM. The speed in this type of motor has traditionally been altered by having additional sets of coils or poles in the motor that can be switched on and off to change the speed of magnetic field rotation. However, developments in power electronics mean that the frequency of the power supply can also now be varied to provide a smoother control of the motor speed. This kind of rotor is the basic hardware for induction regulators, which is an exception of the use of rotating magnetic field as pure electrical application. Polyphase cage rotor. Most common AC motors use the squirrel cage rotor, which will be found in virtually all domestic and light industrial alternating current motors. The squirrel cage refers to the rotating exercise cage for pet animals. The motor takes its name from the shape of its rotor windings, a ring at either end of the rotor, with bars connecting the rings running the length of the rotor. It is typically cast aluminum or copper poured between the iron laminates of the rotor, and usually only the end rings will be visible. The vast majority of the rotor currents will flow through the bars rather than the higher resistance and usually varnished laminates. Very low voltages at very high currents are typical in the bars and end rings. High-efficiency motors will often use cast copper to reduce the resistance in the rotor. In operation, the squirrel cage motor may be viewed as a transformer with a rotating secondary. When the rotor is not rotating in sync with the magnetic field, large rotor currents are induced. The large rotor currents magnetize the rotor and interact with the stator's magnetic fields to bring the rotor almost into synchronization with the stator's field. An unloaded squirrel cage motor at rated no-load speed will consume electrical power only to maintain rotor speed against friction and resistance losses. As the mechanical load increases, so will the electrical load. The electrical load is inherently related to the mechanical load. This is similar to a transformer, where the primary's electrical load is related to the secondary's electrical load. This is why a squirrel cage blower motor may cause household lights to dim upon starting, but does not dim the lights on startup when its fan belt is removed. Furthermore, a stalled squirrel cage motor will consume current limited only by circuit resistance as it attempts to start, unless something else limits the current. Overheating and destruction of the winding insulation is the likely outcome. Virtually every washing machine, dishwasher, standalone fan, a record player, etc., uses some variant of a squirrel cage motor. Polyphase wound rotor, an alternate design, called the wound rotor, is used when variable speed is required. In this case, the rotor has the same number of poles as the stator and the windings are made of wire, connected to slip rings on the shaft. Carbon brushes connect the slip rings to a controller such as a variable resistor that allows changing the motor's slip rate. In certain high-power variable-speed wound rotor drives, the slip frequency energy is captured, rectified, and returned to the power supply through an inverter. With bidirectionally controlled power, the wound rotor becomes an active participant in the energy conversion process, with the wound rotor doubly fed configuration showing twice the power density. Compared to squirrel cage rotors, wound rotor motors are expensive and require maintenance of the slip rings and brushes, but they were the standard form for variable speed control before the advent of compact power electronic devices. Transistorized inverters with variable frequency drive can now be used for speed control, and wound rotor motors are becoming less common. Several methods of starting a polyphase motor are used. Where a large inrush current and high starting torque can be permitted, the motor can be started across the line, by applying full line voltage to the terminals. Where it is necessary to limit the starting inrush current, the motor is started at reduced voltage using either series inductors, an autotransformer, thyristors, or other devices. A technique sometimes used is star-delta starting, where the motor coils are initially connected in star configuration for acceleration of the load, then switched to delta configuration when the load is up to speed. This technique is more common in Europe than in North America. Transistorized drives can directly vary the applied voltage as required by the starting characteristics of the motor and load. This type of motor is becoming more common in traction applications such as locomotives, where it is known as the asynchronous traction motor. Two-phase servo motor. A typical two-phase AC servo motor has a squirrel cage rotor and a field consisting of two windings. A constant voltage main winding, a control voltage winding in quadrature with the main winding so as to produce a rotating magnetic field. Reversing phase makes the motor reverse. An AC servo amplifier, a linear power amplifier, feeds the control winding. The electrical resistance of the rotor is made high intentionally so that the speed-torque curve is fairly linear. Two-phase servo motors are inherently high-speed, low-torque devices, heavily geared down to drive the load. Single-phase induction motor. Single-phase motors do not have a unique rotating magnetic field like multi-phase motors. The field alternates between pole pairs and can be viewed as two fields rotating in opposite directions. They require a secondary magnetic field that causes the rotor to move in a specific direction. After starting, the alternating stator field is in relative rotation with the rotor. Several methods are commonly used. Shaded pole motor. A common single-phase motor is the shaded pole motor and is used in devices requiring low starting torque, such as electric fans, small pumps, or small household appliances. In this motor, small single-turn copper shading coils create the moving magnetic field. Part of each pole is encircled by a copper coil or strap. The induced current in the strap opposes the change of flux through the coil. This causes a time lag in the flux passing through the shading coil, so that the maximum field intensity moves across the pole face on each cycle. This produces a low-level rotating magnetic field which is large enough to turn both the rotor and its attached load. As the rotor picks up speed, the torque builds up to its full level as the principal magnetic field is rotating relative to the rotating rotor. A reversible shaded pole motor was made by Barbara Coleman several decades ago. It had a single field coil and two principal poles, each split halfway to create two pairs of poles. Each of these four half poles carried a coil, and the coils of diagonally opposite half poles were connected to a pair of terminals. One terminal of each pair was common, so only 3 terminals were needed in all. The motor would not start with the terminals open. Connecting the common to one other made the motor run one way, and connecting common to the other made it run the other way. These motors were used in industrial and scientific devices. An unusual, adjustable speed, low-torque shaded pole motor could be found in traffic light and advertising lighting controllers. The pole faces were parallel and relatively close to each other, with the discs centered between them, something like the disc in a watt-hour meter. Each pole face was split, and had a shading coil on one part. The shading coils were on the parts that faced each other. Both shading coils were probably closer to the main coil. They could have both been farther away, without affecting the operating principle, just the direction of rotation. Applying AC to the coil created a field that progressed in the gap between the poles. The plane of the stator core was approximately tangential to an imaginary circle on the disc, so the traveling magnetic field dragged the disc and made it rotate. The stator was mounted on a pivot so it could be positioned for the desired speed and then clamped in position, keeping in mind that the effective speed of the traveling magnetic field in the gap was constant. Placing the poles nearer to the center of the disc made it run relatively faster, and toward the edge, slower. It is possible that these motors are still in use in some older installations. Split-phase motor. Another common single-phase AC motor is the split-phase induction motor, commonly used in major appliances such as air conditioners and clothes dryers. Compared to the shaded pole motor, these motors provide much greater starting torque. A split-phase motor has a secondary start-up winding that is 90 electrical degrees to the main winding, always centered directly between the poles of the main winding, and connected to the main winding by a set of electrical contacts. The coils of this winding are wound with fewer turns of smaller wire than the main winding, so it has a lower inductance and higher resistance. The position of the winding creates a small phase shift between the flux of the main winding and the flux of the starting winding, causing the rotor to rotate. When the speed of the motor is sufficient to overcome the inertia of the load, the contacts are opened automatically by a centrifugal switch or electric relay. The direction of rotation is determined by the connection between the main winding and the start circuit. In applications where the motor requires a fixed rotation, one end of the start circuit is permanently connected to the main winding, with the contacts making the connection at the other end. Capacitor start motor. A capacitor start motor is a split-phase induction motor with a starting capacitor inserted in series with the start-up winding, creating an LC circuit which produces a greater phase shift than both split-phase and shaded pole motors. Resistance start motor. A resistance start motor is a split-phase induction motor with a starter inserted in series with the start-up winding, creating reactance. This added starter provides assistance in the starting and initial direction of rotation. Permanent split capacitor motor. Another variation is the permanent split capacitor motor, also known as a capacitor-run motor. This type of motor uses a non-polarized capacitor with a high voltage rating to generate an electrical phase shift between the run and start windings. PSC motors are the dominant type of split-phase motor in Europe and much of the world, but in North America, they are most frequently used in variable torque applications and other cases where variable speeds are desired. A capacitor with a relatively low capacitance and relatively high voltage rating is connected in series with the start winding and remains in the circuit during the entire run cycle. Like other split-phase motors, the main winding is used with a smaller start winding, and rotation is changed by reversing the connection between the main winding and the start circuit. There are significant differences, however. The use of a speed-sensitive centrifugal switch requires that other split-phase motors must operate it, or very close to, full speed. PSC motors may operate within a wide range of speeds, much lower than the motor's electrical speed. Also, for applications like automatic door openers that require the motor to reverse rotation often, the use of a mechanism requires that a motor must slow to a near stop before contact with the start winding is re-established. The permanent connection to the capacitor in a PSC motor means that changing rotation is instantaneous. Three-phase motors can be converted to PSC motors by making common two windings and connecting the third via a capacitor to act as a start winding. However, the power rating needs to be at least 50% larger than for a comparable single-phase motor due to an unused winding.